It begins without warning. A massive star, far larger than our sun, reaches the end of its life, and in a moment no telescope can predict. It unleashes the most powerful explosion the universe can produce, a gamma-ray burst. Invisible, fast, and deadly, this pulse of radiation can travel across galaxies in silence. And one star, known as WR104, might already be aiming such a burst at Earth. It's a ticking time bomb, spinning at incredible speed, and when it finally collapses, we may not even see it coming until it's too late. If you're fascinated by cosmic mysteries, dying stars, and the hidden dangers of deep space, you're in the right place. Make sure to subscribe and join me on this journey through the most extreme forces in the universe. Because the more we understand, the better prepared we'll be for what's out there. This is the silent threat of gamma-ray bursts. It begins without warning. A massive star, hundreds of times larger than our sun, reaches the end of its life. And in a moment no telescope could predict, it detonates in the most violent explosion the universe can produce. Across the vacuum of space, something moves. It is not visible light, not yet. It's a pulse of radiation, invisible and deadly, traveling at the speed of causality itself. In less than 8 minutes, the light will reach Earth, but before the brightness arrives, the high-energy wavefront comes first. A gamma-ray burst, twin jets of tightly focused radiation slice through the cosmos like cosmic scalpels. This is no ordinary supernova. It is a long-duration gamma-ray burst, triggered by a collapsing massive star, one with extreme mass, spin, and instability. If aimed directly at Earth, even from thousands of light years away, it could sterilize our upper atmosphere. But not all massive stars are this dangerous. To threaten Earth, the star must meet specific criteria: mass, proximity, and orientation. And there are only a handful of such candidates in our galactic neighborhood. One of them is known as WR104, a Wolf-Rayet star located about 7,500 light years away in the constellation Sagittarius. It's one of the most unstable stars ever observed, and its axis appears possibly to be pointed right at us. WR104 is what astronomers call a ticking time bomb, a binary system stripped of its hydrogen shell, spinning at immense speed. The conditions are almost perfect for a GRB upon core collapse. The star itself is nearly 25 times the mass of the Sun, but that's just the visible portion. Its inner structure contains an iron core nearing catastrophic collapse. At the end of its life, it will collapse inward, then rebound outward in a titanic shockwave. This rebound releases more energy in a few seconds than our Sun will release in its entire 10 billion year lifespan. But the real danger is not the blast, it's the jet. If WR104 emits a gamma-ray burst aimed at Earth, it would arrive before we even knew what had happened. Gamma-ray bursts are among the brightest events in the universe, but their danger comes not from light, but from radiation. The gamma rays break molecular bonds in Earth's upper atmosphere, specifically the ozone layer. Without the ozone layer, ultraviolet radiation from the Sun would reach the surface unfiltered. Not immediately fatal, but over weeks or months, this radiation would destroy ecosystems, disrupt DNA, and collapse agriculture. The planet wouldn't explode, but life would begin to suffocate in slow motion. To understand the true risk, we need to examine what happens inside a dying star. Massive stars burn through nuclear fuel in their cores, hydrogen, then helium, then heavier elements. Eventually, iron builds up at the core, and that's when fusion stops producing energy. Iron doesn't fuse, it consumes energy. So the star's core becomes a runaway collapse. Gravity crushes it inward, forming either a neutron star or a black hole. As the outer layers fall inward and rebound, the star explodes in a supernova. If the star has the right spin and mass, this collapse forms an accretion disk around the core. Magnetic fields wind up, and twin jets of plasma and gamma radiation blast out along the poles. These jets are collimated, meaning they are tightly focused, like a laser beam. Only a small percentage of supernova produce gamma-ray bursts. But when they do, and when the beam is aimed at Earth, the consequences are catastrophic. If such a burst occurred tomorrow from WR-104, the gamma radiation would reach Earth in 7,500 years, the time it takes light to travel that distance. But the star could have exploded 7,499 years ago, and we'd find out tomorrow. The sky would suddenly flash with a pinpoint of extreme light, visible even during the day. Telescopes would detect it first, then satellites. Radiation levels in the upper atmosphere would spike, and shortly after we would see UVB levels on the surface begin to rise. Within hours, satellites could be disabled. The ionosphere would be flooded with radiation, disrupting GPS, radio, and power systems. Airliners would be forced to land to protect passengers from excessive exposure. Within days, the chemistry of the atmosphere would change. Nitrogen oxides would build up, creating a thin haze across the globe. The skies would dim slightly, but the real danger would come from the sun itself. With the ozone layer compromised, ultraviolet rays would reach the surface in unprecedented amounts. Crops would begin to fail. The base of the food chain, plankton, algae, surface bacteria, would collapse first. Humans would survive, but at great cost. Sunscreen and protective gear would become mandatory outdoors. But it's the long-term ecological collapse that would define the event. And yet, it might already be on its way. A cosmic bullet fired millennia ago, still traveling through the dark. We simply wouldn't know until the moment it hits. The first layer to feel the impact is the stratosphere. This is where the protective ozone layer sits, shielding Earth from solar ultraviolet radiation. When the gamma-ray burst hits, it begins to break apart the molecular bonds of ozone instantly. Ozone, OV, is highly reactive. The incoming radiation splits it into oxygen O and free oxygen atoms. These free atoms then react with nitrogen, forming nitrogen oxides molecules that further destroy ozone. This is called a catalytic cycle. It doesn't just damage ozone, it prevents it from reforming. One burst of gamma rays can strip away 50% of the ozone layer within days. The effects vary depending on Earth's latitude and season. The polar regions are already vulnerable due to thin ozone. But mid-latitudes and equatorial regions would also suffer severe depletion. Without ozone, the sun becomes dangerous. Ultraviolet B radiation, which is normally filtered, now floods the surface. This radiation causes direct DNA damage in plants, animals, and humans. Phytoplankton in the oceans die first. They make up the base of the marine food chain and produce much of Earth's oxygen. A sudden drop in plankton collapses fish populations within weeks. Next, land-based ecosystems begin to break down. Plants exposed to excess UV radiation lose chlorophyll efficiency. Photosynthesis slows, food chains contract, and biodiversity declines. Insects, amphibians, and small mammals are hit hard. Their short lifespans and reproductive cycles leave them vulnerable to rapid environmental change. Extinction rates begin to climb, even in protected zones. For humans, the effects are slower but no less serious. Increased UV exposure leads to higher cancer rates, cataracts, and immune system suppression. Agriculture declines as staple crops fail or must be grown. Indoors under artificial lighting, the climate begins to change not from the GRB directly, but from its secondary effects. Nitrogen oxides and atmospheric haze reduce the amount of solar energy reaching the ground. This causes a short-term global cooling effect, similar to volcanic winter. Rainfall patterns shift, jet streams weaken, and weather systems stall, leading to droughts in some regions and floods in others. Food insecurity spreads. Regions reliant on agriculture become unstable. Governments begin rationing, and international supply chains falter. Technology is no escape. Satellites damaged by ionospheric disturbances begin to fail. GPS, internet, and communications degrade day by day. Power grids are vulnerable. Transformer stations, overloaded by radiation spikes and magnetic disturbances, go offline. Blackouts spread in waves across continents. Global infrastructure begins to unravel not from a single explosion, but from its cascading consequences. Hospitals, reliant on supply chains and power, struggle to treat rising illness rates. Cities become vulnerable as logistics break down. And yet, life continues. Not everywhere, and not in every form, but some species endure. Microorganisms, deep sea life, and organisms shielded underground survive untouched. These survivors become the seeds of ecological recovery. But the timeline is long, decades to centuries. Recovery depends not just on biology, but on the stability of climate, atmosphere, and solar exposure. Astronomers begin to calculate the origin of the burst. Using satellite triangulation, they trace the incoming radiation's direction back to Sagittarius. The coordinates match a known object, WR104. The confirmation comes within hours. Telescopes verify that WR104 is no longer visible in its previous form. Its spectrum has shifted, replaced by an expanding cloud of gas and stellar remnants. A core collapse supernova confirmed. But unlike others, this one included a directed gamma-ray burst. And Earth was directly in the path. The realization echoes across observatories worldwide. This wasn't a coincidence, it was an inevitable cosmic alignment. And Earth happened to lie in the crosshairs of a 7,500-year-old explosion. The media begins to report it, slowly and cautiously. Not because the danger is unknown, but because it's already over. The radiation has already passed, and the damage is already in motion. There is no next wave coming. There is no second flash. This was a one-time burst, and now humanity must adapt. Agencies begin immediate atmospheric sampling. Weather balloons, satellites, and high-altitude aircraft collect data on UV levels and ozone loss. Within days, global UV alerts are issued. Citizens are instructed to stay indoors during daylight hours. Protective clothing becomes standard. Outdoor agriculture is suspended or relocated to controlled environments. The GRB becomes a defining historical event. It is given a name, a time, and a spectral ID. And Earth enters a new chapter, a post-burst civilization. Not all dying stars are capable of creating gamma-ray bursts. Most stars, including our Sun, will end their lives quietly as white dwarfs, shedding outer layers in gentle waves. But the universe reserves something more violent for its largest, fastest spinning giants. The gamma-ray burst, especially the long-duration kind, is not just a supernova. It's a rare, narrowly focused release of relativistic energy. It forms only under the most extreme internal conditions in a collapsing massive star. The star must be at least 20 times the mass of the Sun. It must have shed its outer hydrogen shell, exposing its helium or carbon-oxygen core. And it must be rotating at an extraordinary speed. This spin is essential. As the core collapses, conservation of angular momentum causes the rotation rate to skyrocket. The faster the spin, the stronger the resulting magnetic fields. Inside the collapsing star, matter falls inward at relativistic speeds. A black hole may form at the core, or in some cases, a magnetar, a hypermagnetized neutron star. Around this, an accretion disk builds a dense, hot ring of gas spiraling at nearly light speed. Magnetic field lines twist and snap. They funnel plasma away from the poles, where resistance is lowest. This is where the jets form two beams of focused radiation and matter, traveling near the speed of light. These jets must punch through the dying star's outer layers. If the star is too thick, they stall inside. But if the envelope is thin like in a Wolf-Rayet star, they escape. This is why WR stars are prime candidates. They've lost their outer shells due to stellar winds or binary interactions. What remains is a stripped, volatile core, a perfect launching pad for a GRB dot. As the jet emerges, it releases gamma rays in tight beams only a few degrees wide. This means that for every gamma ray burst we detect, there are hundreds more we never see. Most explode in darkness, pointing somewhere else. But if Earth lies in the path, we get the full force of the event. The brightness of the gamma ray burst is so intense, it can outshine entire galaxies for seconds. Its energy is concentrated, not dispersed, making it dangerous over much greater distances. Astronomers classify GRBs by duration and energy profile. Long-duration bursts come from collapsing stars and last from 2 seconds to several minutes. Short-duration bursts are likely from neutron star mergers and behave differently. In both cases, relativistic jets are key. The extreme physics at the core involve general relativity, quantum mechanics, and high-energy plasma interactions. We are still unraveling the exact dynamics, even today. Computer simulations model jet formation using magnetohydrodynamics. These equations combine the behavior of magnetic fields with fluid dynamics under relativistic conditions. They predict how the jets evolve, what radiation they produce, and how they interact with the surrounding material. The jet interacts with interstellar gas as it travels outward. This creates a glowing aftershock called an afterglow, visible in X-rays, optical, and radio. It can last days, weeks, or even months, slowly fading as the energy disperses. Telescopes on Earth and in orbit track these afterglows. They help determine distance, structure, and orientation. Combined with the initial burst data, they paint a picture of the original explosion. This is how WR-104's potential danger was assessed. Astronomers noted its rotation axis may be aligned toward Earth. If true, and if the conditions inside the star are right, a future collapse could send a jet directly at us. But that alignment is still uncertain. Estimates vary by a few degrees, and even a slight offset could spare us entirely. Nonetheless, the star remains a subject of intense monitoring. Gamma ray bursts are rare in our galaxy. Most we detect come from billions of light years away, in distant galaxies. But all it takes is one in our own backyard to change history. WR-104 is not alone. Other nearby Wolf-Rayet stars like WR-112 and WR-93b also pose theoretical risks. None are guaranteed to explode soon, but the timelines are measured in thousands of years, not millions. And we may not see it coming. Wolf-Rayet stars show only subtle signs of instability before collapse. There may be no visible warning, just silence, followed by light. That's the nature of gamma ray bursts. They are the universe's most sudden catastrophe. And even in their rarity, they hold consequences far beyond their origin. Modern astronomy operates like a vast, interconnected network of sentinels. Dozens of space-based and ground-based observatories scan the skies every second. Their job is not just to discover distant stars, but to monitor known threats. Instruments like SWIFT, Fermi, and Integral specialize in detecting gamma ray activity. They're designed to sense high-energy bursts within seconds of arrival. When a burst occurs, these telescopes send out global alerts triggering follow-up from optical and radio observatories worldwide. This rapid response system is called the Gamma Ray Coordinates Network, GCN. It allows scientists to localize the burst, identify its origin, and track the afterglow across the spectrum. But it only works after the burst has already happened. There's no pre-burst warning system. No instrument can currently detect a gamma ray burst before it strikes. Because the light and radiation travel at the same speed, we receive the information only as it arrives. Telescopes monitor candidates like WR104 using spectroscopy and photometry. They measure surface temperature, rotation rate, and chemical composition. These readings help estimate how close a star is to collapse, but they can't predict the exact moment. A star may appear stable right up until core failure. There might be no visible change, no fluctuation in brightness, no ejected gas. Then, without warning, it collapses and releases its energy in all directions. This unpredictability is what makes GRBs uniquely difficult to defend against. We have early warning systems for solar flares, asteroid impacts, and even supernova in nearby galaxies. But gamma-ray bursts, if aimed directly at Earth, offer no lead time. Efforts are underway to improve monitoring of high-risk stars. New infrared telescopes are being developed to observe stars, even through dense cosmic dust. These may give us better data on stellar rotation and binary dynamics. Next generation observatories like the Vera C. Rubin Observatory will track the entire visible sky every few nights. This rapid cadence will help detect subtle variability in stars that may hint at pre-collapse activity. Still, those clues would come hours or minutes before the main event. At best, we might receive a few hours of strange behavior, a dip in brightness, or a sudden infrared spike. But even then, it wouldn't be clear what was coming until the radiation arrived. Satellites in Earth orbit would feel it first. Radiation detectors would spike. And within moments, alerts would flood through scientific networks. Space weather centers would scramble to assess the threat. Ionospheric models would update in real time. Governments would be notified and radiation exposure levels monitored. But the burst would already be in progress. No technology on Earth could stop it. The only option would be emergency mitigation shelter, isolation, and damage control. It's worth noting that gamma-ray bursts fade quickly. The main pulse lasts seconds to minutes. The afterglow can linger, but it's much less dangerous. Still, that short pulse is enough to change everything. It can break down ozone, seed the upper atmosphere with nitrogen compounds, and disrupt global climate for years. And by the time we understand what happened, it's already in the past. Unlike an asteroid or a solar flare, a gamma-ray burst is silent. It makes no noise. It announces itself with destruction. Could we build a true early warning system? In theory, yes, but it would require constant, real-time observation of thousands of massive stars. It would also demand predictive models far beyond what we currently possess. Most gamma-ray bursts occur in distant galaxies, billions of light years away, where they pose no threat. But all it takes is just one, in the wrong direction. WR104 remains under surveillance. But with only limited data on its spin axis, we can't be certain of its orientation. That uncertainty is the thin line between harmless light and atmospheric devastation. Astronomy is improving. New telescopes are coming. But for now, gamma-ray bursts remain the only astrophysical threat we cannot see coming. Earth's surface carries scars from eons of cosmic violence. Meteorite impacts are easy to detect: craters, shocked quartz, iridium layers. But radiation events like gamma-ray bursts leave no craters, only chemical signatures. To find them, scientists search the sedimentary record. They look for sudden spikes in nitrate compounds and radioisotopes in ancient rock layers. These are telltale markers of high energy radiation interacting with Earth's atmosphere. One candidate stands out: the Ordovician-Silurian extinction, around 443 million years ago. It was one of the 5 major extinction events in Earth's history. Roughly 85% of marine species vanished in a geologically short time. Paleoclimatic evidence shows a sharp, sudden cooling of the planet. This glaciation doesn't match volcanic or asteroid signatures. Instead, researchers have proposed a gamma-ray burst as a trigger. A powerful GRB could have stripped the ozone layer within days. Ultraviolet radiation would flood the oceans, especially the photic zone where plankton live. Massive losses in primary producers would ripple upward, collapsing the entire marine ecosystem. Climate change would follow. The introduction of nitrogen oxides into the stratosphere would trigger a chemical winter. Cooling oceans would destabilize thermal currents, affecting everything from reefs to continental shelf life. But confirming a GRB from that long ago is difficult. Radiation doesn't leave a clear fossil. It alters chemistry, but only for a moment. Still, scientists have found nitrate anomalies in deep sea cores from similar periods. These match what we'd expect from a brief but intense ionizing event. But the resolution is low, and the data remain inconclusive. There's also evidence from the late Devonian period, around 360 million years ago. Another extinction this. One slower, but possibly radiation-related. Spores from that era show deformities, consistent with UV damage. These mutations hint at elevated ultraviolet radiation for extended periods. If the ozone layer had been compromised, it would explain the biological stress. And again, a gamma-ray burst fits the physical model. However, alternative explanations exist. Volcanism, ocean anoxia, and asteroid impacts are also part of the extinction toolkit. No one cause can be declared definitive without stronger geochemical evidence. Still, the possibility remains. Gamma-ray bursts, though rare, have the energy to cause extinction-level effects. And Earth's history may include more than one such event. Today, we monitor stars because of this ancient lesson. It's not just theoretical risk, it may be part of our evolutionary past. Life on Earth may have been reset by light. Even recent history offers clues. In 1998, satellites detected a burst of gamma rays from the magnetar, SGR 1900+14. It came from over 20,000 light-years away, and still ionized part of Earth's upper atmosphere. It wasn't a GRB, it was a soft gamma repeater, far less powerful. Yet it showed that distant stellar events can influence our planet. Even minor outbursts leave fingerprints on the ionosphere. This means the threshold for atmospheric response is low. Earth's systems are sensitive to high-energy radiation, and major bursts thousands of times stronger could leave lasting geochemical markers. If another GRB hit Earth in recorded history, we might miss it entirely. No visible destruction, no impact crater. Just a sudden shift in UV radiation, climate, and biology. Our ancestors would not have known what caused it. There would be no myth, no record, no warning. Only plagues of dying crops, skin disease, and mysterious environmental collapse. But science today gives us hindsight. We can model these events, compare the evidence, and simulate outcomes. And we now understand that gamma-ray bursts are not just distant fireworks, they are agents of planetary change. Of the more than 200 billion stars in the Milky Way, only a small subset are candidates for gamma-ray bursts. These are stars at least 20 times more massive than the Sun, with high rotational speed and low metallicity. They must also be stripped of their outer hydrogen layers, often via stellar winds or binary interaction. The most dangerous type of all is the Wolf-Rayet star. These are hot, massive stars nearing the end of their lives. They have lost their hydrogen shells and burn helium, or heavier elements in their cores. Wolf-Rayet stars are rare, but they are concentrated in regions of intense star formation, including some within 10,000 light-years of Earth. Of these, a handful have drawn serious attention from astronomers. At the top of that list is WR104, located about 7,500 light-years away in the Sagittarius arm of the Milky Way. It is a binary system. Its primary star is a textbook GRB, candidate massive, fast-spinning, and in the final stages of its stellar life. WR104 also appears to be pointed directly at Earth. Infrared imagery shows a corkscrew-shaped spiral of dust created as the binary system orbits. This spiral suggests that the rotational axis, and therefore any future, gamma-ray jet may be aligned with us. But that orientation is not fully confirmed. Small observational uncertainties mean we could be a few degrees off axis. And just a slight deviation could mean complete safety. Another candidate is Eta Carini, located about 7,600 light-years away in the Carina constellation. It's one of the most massive binary systems known, with a combined mass exceeding 100 solar masses. Its 19th century outburst, the Great Eruption, released as much light as a supernova, but did not destroy the star. Eta Carini is unstable. It could go supernova within the next million years. However, most models suggest it is unlikely to produce a gamma-ray burst due to its high metallicity and uncertain spin axis. WR93b, another Wolf-Rayet star in Scorpius, is roughly 10,000 light-years away. It shares many properties with WR104 fast spin, stripped outer layers, and high luminosity. But less is known about its orientation and mass loss rate. Then there's WR112, about 5,200 light-years away, notable for its dusty pinwheel structure. Its binary orbit has also created a visible spiral of material. It too is under close monitoring, though no GRB signature has been confirmed. One of the closest massive stars is Betelgeuse, just 642 light-years away. It's a red supergiant, nearing the end of its life, and it will go supernova relatively soon on a cosmic timescale. But it lacks the speed and structure needed to generate a gamma-ray burst, so it poses no radiation threat to Earth. Despite dramatic headlines, no known star closer than WR104 is a credible GRB risk. The vast majority of supernova do not emit gamma-ray jets, and most jets are not aimed at us. ASTR, OPHYSIC. ICE risk using three main criteria: distance, rotation, and alignment. Even stars with massive cores are harmless if their jets are angled away. And because GRBs are so narrowly beamed, the statistical odds are extremely low. Nonetheless, monitoring continues. Spectroscopic data help track changes in stellar wind, mass loss, and elemental composition. These clues help model how far a star is from core collapse. The lifespans of such stars are short, just a few million years compared to the Sun's 10 billion. WR104 is likely near the end of its timeline. But near, in astronomical terms, could mean anytime within the next 100,000 years. That margin of uncertainty is vast. The collapse could come tomorrow, or not for tens of thousands of years. Until it happens, the star may show no visible change. What we do know is this: WR104 is unstable, massive, and potentially aimed at us. And if a burst is coming, it already happened 7,500 years ago. We are simply waiting for the light to arrive. The moment the gamma-ray burst reaches Earth, it begins with silence. There is no shockwave, no flash visible to the naked eye, not yet. But the upper atmosphere is already unraveling. In the first 0.1 seconds, gamma photons collide with atmospheric nitrogen and oxygen molecules. These collisions break molecular bonds, releasing free radicals and initiating chain reactions. Ozone molecules begin to split apart immediately. Within 1 second, satellite detectors across the planet register an intense spike in high-energy radiation. Instruments aboard missions like Fermi and Swift trigger emergency alerts. Astrophysical data centers begin receiving real-time spectral analysis. At 3 seconds, the ionosphere's charged upper layer begins to saturate. Long-range radio communications in the high-frequency band experience interference. GPS accuracy drops as satellite signals begin to bend unpredictably. By 10 seconds, polar regions of Earth experience the greatest energy input. The magnetic field focuses incoming radiation near the poles, intensifying atmospheric ionization. Auroral activity spikes, visible even in daylight. At 30 seconds, ozone depletion accelerates in the stratosphere. Gamma rays and resulting nitrogen oxides destroy up to 1% of the protective layer per second in the impacted regions. The atmosphere's ability to block ultraviolet light begins collapsing. By 60 seconds, the first visible effect reaches the ground, a pinpoint of intense light in the sky. To the human eye, it resembles a new star, bright, hard-edged, and unmoving. Observatories immediately triangulate the source, Sagittarius, exactly where WR-104 sits. Within 2 minutes, low Earth orbit satellites begin malfunctioning. Radiation-sensitive components suffer permanent damage. Mission control teams initiate shutdown protocols for non-hardened instruments. At 5 minutes, the gamma-ray pulse ends. The beam has passed, but its damage has only just begun. Nitrogen oxides now flood the stratosphere. These compounds catalyze ozone destruction and remain in the atmosphere for months. They reflect sunlight, altering Earth's radiation budget. Within 15 minutes, international science agencies confirm the burst and issue radiation advisories. Civil aviation halts high-altitude flights. Passengers already airborne are advised to descend or reroute away from polar flight paths. At 1 hour, ultraviolet radiation levels on the surface begin to rise. UVB, normally filtered by ozone, penetrates through the weakened atmospheric shield. Readings exceed safe thresholds across much of the globe. By 6 hours, photochemical reactions begin affecting ground-level air quality. Smog formation accelerates, especially in urban areas with high nitrogen content. Sensitive populations begin reporting respiratory distress. Within 24 hours, global climate monitoring satellites detect a measurable dip in solar energy reaching the surface. Nitrogen oxide haze reflects visible light back into space. Surface temperatures begin to drop slightly, particularly in temperate zones. At 48 hours, agricultural models predict a 20 to 40% increase in ultraviolet exposure across crop-producing regions. Plants with high UV sensitivity, such as wheat, corn, and rice, experience photosynthetic stress. Seedlings wilt. Growth slows. By day 3, plankton populations in sunlit ocean layers decline sharply. These microscopic organisms form the base of the marine food web. Their collapse affects fish populations, carbon cycling, and ocean oxygen production. Within 1 week, the global UV index reaches extreme levels in equatorial and mid-latitudes. Human outdoor activity becomes restricted. Protective clothing, UV shelters, and sunblock distribution are mandated in multiple nations. By 2 weeks, atmospheric modeling confirms a 35 to 60% reduction in global ozone, depending on latitude. The full extent of the gamma-ray burst's chemical footprint becomes clear. Earth's radiation shield is not just damaged, it's broken. At 1 month, ecosystems begin collapsing. Insect populations, particularly pollinators like bees, suffer catastrophic losses. This cascades into food production failures and agricultural collapse. By day 45, global supply chains face strain. Indoor farming, vertical agriculture, and hydroponics ramp up, but cannot match demand. Food prices spike. Water systems become stressed. Within 2 months, governments issue coordinated ultraviolet exposure policies. People remain indoors during daylight hours. Work, travel, and recreation are reorganized around the new solar threat. By 3 months, respiratory diseases, cancers, and immune dysfunction rise due to increased radiation exposure. Skin cancer diagnoses double in some regions. Health systems begin to buckle under sustained environmental stress. The ecological effects are worse in high-altitude and low-latitude regions. Rainforests suffer defoliation. Mountain species go Extinct as UV exposure becomes lethal, even in cloud-covered areas. At 6 months, a pseudo-nuclear winter effect begins. Reduced sunlight and climate destabilization lead to global cooling of -2 degrees Celsius. Some regions experience failed monsoon seasons. Others prolong drought. After 1 year, the worst is over. But recovery is slow and incomplete. Ozone regeneration, driven by slow photochemical reactions, takes decades. The biosphere reconfigures itself around the damage. Some species adapt, others vanish. Human civilization survives, but altered, more cautious, more sheltered. All of it traced back to one star, one collapse, one beam of energy that crossed 7,500 light years to reach us. By day 100, humanity begins shifting from reaction to long-term response. Immediate radiation concerns have stabilized, but the consequences linger. Governments convene with international agencies to coordinate global adaptation strategies. United Nations declares a planetary emergency under its Office for Outer Space Affairs. The World Health Organization, FAO, and WMO lead efforts to manage food, health, and climate systems. New global protocols are enacted for radiation-safe urban planning and ultraviolet shielding. The most immediate concern is agriculture, with surface crops suffering under extreme UV exposure. Nations ramp up controlled environment agriculture. Greenhouses, underground farms, and hydroponic systems become the backbone of food supply. Silicon Valley and East Asia invest rapidly in vertical farming, stacked agricultural towers with LED lighting. These systems allow constant food production without solar exposure. Carbon emissions drop, but energy demand skyrockets. Power grids are restructured to support indoor infrastructure. Solar panels, ironically, become less effective under atmospheric haze. Nuclear, geothermal, and fusion pilot plants begin scaling faster than anticipated. Cities shift toward UV-mitigated architecture. Reflective materials and UV-blocking polymers are added to building exteriors and windows. Public outdoor hours are restricted to twilight and night, creating a reversal of human activity cycles. Clothing standards change. UV-proof garments become standard. Children wear full coverage gear during limited outdoor exposure. Schools operate under artificial light, often underground or in shielded structures. Air travel is restructured. High-altitude flight paths are eliminated due to atmospheric exposure. Suborbital vehicles and radiation-shielded aerospace corridors are proposed but remain years away from implementation. Global communication systems undergo emergency upgrades. Radiation-hardened satellites are launched to replace those damaged. During the burst, a new class of LEO constellations includes built-in shielding and autonomous rerouting capabilities. Healthcare systems face long-term ultraviolet complications. Skin cancer rates remain elevated despite shielding. UV-induced eye damage and immune suppression continue to challenge vulnerable populations. To counter this, the biomedical sector advances synthetic melanin treatments and DNA repair therapies. Gene editing tools like CRISPR are tested to enhance radiation resistance in crops and humans. Prophylactic skin treatments become part of daily public health. Attention then turns to the atmosphere. Models predict that full ozone recovery will take 10 to 15 years, even under optimal conditions. But if nitrogen oxide levels remain high, that timeline stretches past a human generation. Geoengineering is no longer theoretical. Aerosol injection proposals are fast-tracked for deployment. Calcium carbonate and reflective particles are dispersed into the stratosphere to block solar UV temporarily. This artificial shield buys time. It lowers surface temperatures and limits additional ozone degradation. But it also risks disrupting precipitation patterns and causing further ecological imbalance. To address this, a global atmospheric coordination center is formed. Using supercomputing forecasts, it manages chemical payloads and tracks climatic feedbacks in real time. This center becomes a new arm of the UN, akin to a planetary thermostat. Meanwhile, deep-sea ecosystems offer some hope. Shielded by water, marine life below 200 meters remains stable. These ecosystems are studied for genetic resilience, possibly seeding recovery in devastated coastal zones. Public knowledge shifts toward astronomy. School curricula worldwide now include stellar classification, gamma-ray physics, and atmospheric science. A new generation grows up under artificial skies, intimately aware of stellar risk. Art, literature, and culture reflect the change. Sunlight becomes symbolic of fragility and power. Human civilization, once defined by its mastery of light, is now shaped by its defense against it. Space policy changes too. Nations and private firms collaborate on telescopes with 360-degree GMM array surveillance. Real-time GRB monitoring becomes as critical as seismic or weather forecasting. The Gamma Early Alert Network, GEAN, is established. Satellites equipped with high-speed radiation detectors patrol in sun-synchronous orbits. Within seconds of a detected burst, GEAN can calculate trajectory and issue planetary alerts. Even with this system, the window for action remains short. But humanity now understands the stakes, and planetary defense shifts beyond asteroids and solar storms to include collapsing stars. On the ground, ecosystems adapt. Mutations accumulate rapidly in fast-replicating species. New forms of UV-resistant microbes begin to dominate freshwater and coastal environments. Evolution accelerates. Species that survive the radiation are hardier, leaner, and behaviorally different. Insects evolve thicker exoskeletons. Plants adapt narrower leaves and reflectant pigments. The Earth that emerges after 1 year is still habitable but altered. The skies are hazier, the light more filtered, the ecosystems more fragile. And above all, humanity is no longer blind to the stars. WR104 is gone. What once was a brilliant, unstable Wolf-Rayet star has collapsed in seconds. Its core imploded, and its outer layers were blasted into space at thousands of kilometers per second. At the center, gravity won. The mass of the core exceeded the neutron degeneracy limit. Matter collapsed into a singularity, forming a stellar mass black hole. For astronomers, this is both a tragedy and an opportunity. The light from the explosion has just reached Earth, but the physical transformation happened 7,500 years ago. We are seeing the aftermath delayed by the distance light must travel. Radio telescopes begin scanning the region. They search for synchrotron emissions from the expanding supernova remnant. These emissions reveal how fast the shockwave is traveling and what it's colliding with. The remnant expands into the interstellar medium. It pushes against gas and dust, compressing them into filamentary structures. Over time, this can trigger new waves of star formation in the region. High-energy X-ray telescopes study the shock front. They reveal turbulent gas moving at relativistic speeds. These observations help refine our models of jet mechanics and stellar collapse. If a pulsar remains unlikely but possible, it may emit regular radio pulses. These pulses give clues about the core's density, rotation, and magnetic field. But if a black hole formed, it will be mostly invisible, detectable only by its gravitational influence. Over decades, the debris cloud will cool and expand. Heavy elements, iron, nickel, cobalt created during the explosion will seed the local region. These materials may one day become part of new stars and planets. Astronomers will catalog the remnant with high precision. Parallax measurements will refine its distance. Spectroscopy will identify the composition of its expanding shell. This shell, known as a supernova remnant, will glow in multiple wavelengths for centuries. It will resemble the Crab Nebula or Cassiopeia, a colorful, turbulent, and expanding. It becomes a permanent feature of deep sky observation. Its jet trajectory is mapped precisely. Using data from the gamma-ray burst, scientists model the opening, angle, energy profile, and beaming characteristics. These models refine our understanding of which stars are likely to produce future GRBS. Stellar evolution models are updated. WR104 becomes a case study, one of the first detailed GRBs from a known progenitor. It bridges theory and observation, helping validate decades of astrophysical predictions. Gravitational wave detectors such as LIGO and Virgo begin searching archival data. Although GRBs rarely produce strong gravitational waves, the collapse could have generated a faint signal. If found, it would provide a rare multi-messenger detection, light, radiation, and gravity from the same event. Over the next 100 years, the supernova remnant will expand tens of light years. It may encounter molecular clouds, creating regions of turbulence and compression. This interaction seeds the birth of new stars, a cosmic cycle reset by violent death. Future telescopes will return to the site regularly. Generations of astronomers will track its evolution, like watching the ripples of an ancient explosion spread across time. The black hole at its center will remain hidden, silent, massive, and eternal. If it's part of a binary system, the black hole may eventually consume its companion. This could lead to new bursts of X-rays, or even another jet. In such cases, the system becomes an X-ray binary, bright, erratic, and detectable across the galaxy. The region around WR104 will never be the same. It has gone from stellar nursery to radiation hazard to astronomical laboratory. And the aftershocks, both physical and scientific, will continue for centuries. Astronomers will use the data from this event to refine detection algorithms. Machine learning systems will scan star catalogs for other Wolf-Rayet stars with similar properties. The goal: to map every potential GRB source before it detonates. Satellite networks will expand. New detectors will be placed in lunar orbit and at Earth's sun. Lagrange points. Their purpose: to catch the next burst faster, triangulate it more precisely, and understand it more deeply. Cosmic ray observatories also benefit. Some of the highest energy particles from WR104's explosion will arrive decades later. When they strike Earth's atmosphere, they leave traces detected by ground-based instruments, like the Peer Auger Observatory. Each particle adds to our understanding. Each wave of radiation tells a different part of the story. From core collapse to jet formation to afterglow decay, every stage becomes measurable. And from that, humanity builds defense. A deeper understanding of stellar death creates better, predictive tools. We may never prevent a gamma-ray burst, but we can be ready for it. Gamma-ray bursts remain the most luminous high-energy events ever recorded in the universe. Yet despite decades of observation, we still do not fully understand their inner workings. The core mechanisms of jet formation, magnetic field alignment, and particle acceleration remain unsolved. We've cataloged thousands of GRBs, but most are extragalactic, billions of light years away. These offer rich data, but they're too distant to resolve fine details. We need one close enough to study, but far enough to be safe. New instruments are in development to meet this challenge. The Theseus mission by the European Space Agency, planned for launch this decade, will search for high redshift GRBs from the early universe. It will use advanced X-ray and infrared detectors to probe the birth of the first black holes. NASA is developing the Gamma Explorer, a gamma-ray observatory capable of rapid localization of transient events. It will carry a wide-field coated aperture telescope to spot bursts as they happen. This real-time detection will improve follow-up speed dramatically. The Cherenkov Telescope Array, CHETAI, under construction in Chile and Spain, will observe the highest energy photons from GRBs, By detecting gamma rays in the TeV range, it will push the boundaries of what we know about cosmic ray origins. CTA sensitivity will allow scientists to detect the GRB afterglow long after the initial pulse fades. Meanwhile, gravitational wave observatories continue to expand. The proposed Einstein telescope and Cosmic Explorer will detect fainter and more distant mergers, potentially catching events that lead to short-duration GRBs. Combined with gamma-ray detectors, they will offer true multi-messenger astronomy. Another mission, Lynx, is a next-generation X-ray telescope concept under review by NASA. If funded, it will have over 100 times the sensitivity of Chandra. It will allow us to observe the remnants of GRB progenitors in unprecedented detail. Even private space ventures are beginning to contribute. Companies like Rocket Lab are deploying small satellites with gamma-ray sensors into low Earth orbit. Their agility and cost efficiency allow rapid response to new burst detections. On the ground, AI-powered observatories are changing the game. Systems like Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory scan the entire night sky repeatedly, looking for optical signatures of recent bursts. Their automated alert systems reduce human delay and speed up scientific reaction time. In parallel, simulations continue to advance. Supercomputers now model stellar collapse down to millisecond precision. These virtual stars help us understand which configurations of spin, mass, and magnetic field produce GRBs, and which don't. Yet many mysteries remain. Why do only a small fraction of supernova emit GRBs? What sets apart a quiet collapse from one that launches jets across space? We still don't fully understand jet collimation, how such narrow, high-energy beams maintain coherence across thousands of light years. We don't know exactly what role magnetic fields play inside the collapsing star, and we're still refining our understanding of how gamma-ray bursts evolve over time. Every GRB offers new surprises. Some are followed by X-ray plateaus. Others show unexpected polarization patterns, clues that the jet structure may be more complex than we thought. Search continues across the electromagnetic spectrum. Radio telescopes map afterglows long after light fades. Infrared observatories detect dust-shrouded bursts hidden behind stellar nurseries. Even the shape of galaxies that host GRBs is under study. Do certain types of galaxies produce more of these events? Is star formation rate the key driver, or are low metallicity environments more decisive? Meanwhile, back on Earth, risk models improve. Statisticians now use gamma-ray burst catalogs to estimate threat frequency. Their models suggest that a GRB powerful enough to damage Earth may occur once every 500 million years. That's rare, extremely rare, but not impossible. And as we've learned, rare in cosmic terms simply means eventual. So we monitor the skies, not out of fear, but out of understanding. Because gamma-ray bursts are not just threats, they are tools for probing the birth and death of the cosmos. They tell us how stars live and how they die. They reveal the formation of black holes, the behavior of matter under extreme gravity, and the dynamics of relativistic jets. They are the flashbulbs of the universe, brief, brilliant, and deeply informative. And one day we may witness one up close again. Perhaps not in our lifetime, but the sky remembers and the stars never rest. A gamma-ray burst begins with a dying star. Specifically, a massive, rapidly rotating hydrogen strip star, most often a Wolf-Rayet. As its core collapses, a black hole forms and magnetic fields channel material into twin relativistic jets. Jets contain gamma radiation compressed into a narrow beam, just a few degrees wide. If one of those beams intersects Earth, even from thousands of light years away, the consequences are immediate. Ozone molecules in the stratosphere are destroyed, and ultraviolet radiation from the sun increases sharply. In a matter of seconds, Earth's atmospheric chemistry is altered. Nitrogen oxides flood the upper layers, initiating a cascade of ozone loss. This loss persists for months, sometimes years, depending on the burst's energy and location, as UV radiation penetrates. Deeper into the atmosphere, it reaches the surface. Marine ecosystems suffer first. Phytoplankton die, and the food web begins to collapse. Crop yields fall due to DNA damage in plant cells and decreased photosynthetic efficiency. Human health is also impacted. Skin cancer, cataracts, and immune dysfunction increase due to prolonged UV exposure. Outdoor activity becomes dangerous without artificial shielding. The climate system is not immune. Nitrogen oxides and increased albedo from upper atmospheric aerosols reduce solar heating. This causes short-term global cooling, which further disrupts weather patterns, and agriculture. Technology suffers collateral damage. Satellites exposed to high-energy particles experience failure in communication, navigation, and climate monitoring systems. Aviation routes shift away from the poles to reduce radiation exposure to passengers and crew. Earth's magnetic field offers limited protection. It channels radiation toward the poles, but does not block gamma rays. These rays interact with atmospheric particles regardless of geomagnetic shielding. Known candidate stars, like WR104, are monitored continuously. If aligned with Earth, and if their cores collapse under the right conditions, they could produce a beam in our direction. Even a minor misalignment would be enough to spare the planet. Despite their rarity, gamma-ray bursts are considered potential extinction-level events. Statistical models suggest Earth is hit with a damaging GRB roughly once every 500 million years. Geological evidence points to possible GRB involvement in at least one past extinction. Science continues to advance. Space agencies are developing better gamma-ray detectors, rapid alert systems, and multi-wavelength observatories. Artificial intelligence accelerates the processing and interpretation of transient cosmic events. We now understand how to reconstruct a burst from its gamma-ray profile to its optical afterglow and remnant evolution. We can measure the elemental composition of supernova remnants and estimate the energy of their jets. We can model atmospheric chemistry under burst conditions with high precision, yet there are still unknowns. Jet composition, magnetic collimation, and variability in burst signatures remain under investigation. No two gamma-ray bursts are exactly alike. Each one teaches us something new. Each detection refines our parameters and improves our understanding of stellar collapse. And each event, though distant, brings us closer to understanding how the universe evolves. If WR104 exploded tomorrow and Earth stood in the path of its jet, we would not prevent it. The radiation would already be en route, traveling at light speed, arriving without warning. Our only option would be to observe, measure, and adapt. But adaptation is possible. Humanity possesses the scientific tools to respond through agriculture, infrastructure, medicine, and atmospheric modeling. A gamma-ray burst would not end civilization, but it would challenge it. In the long arc of cosmic history, GRBs are rare but transformative. They reset ecosystems, redistribute elements, and reveal the fundamental physics of stellar death. Earth has seen them before and may see them again. The science is not finished. New missions, better detectors, and deeper models will continue to expand our knowledge. And with each discovery, we build not just understanding, but resilience. The universe is not silent. It speaks in bursts, short, violent, brilliant. And science is how we listen.